So, so now we have another talk about performance, and this is a talk from Carl from Codazip. So let me introduce Carl again. So Carl's focus is simple, make CHERI secure and fast. At Codazip, he leads work on low-level software with a strong focus on optimizing RISC-V core performance while maintaining robust security foundations. His perspective is grounded in what actually ships. So let's ship performance processes.
Thank you. So this is going to be more software focused rather than hardware focused. Thank you, John. Let's hope. Okay, perfect.
Okay, thank you, Carl. That was a great presentation.
Thanks. Right.
This on the right.
That one. Right. Hey, right. Okay. So just quick note, obviously in Codazip we've been looking at specifically at Linux and how to optimize our Linux solution. Also on our cores as well. But I will say that the software changes that we've made should be generally applicable to any cores, whatever. Majority of the software is already open sourced. We will push out some extra stuff as well in the near future once we've checked it all actually works properly. So, okay. The other thing, for those who missed previous talk in the CHERI tech, is we are able to do comparisons between our core compiled, the core generated without CHERI and with our CHERI variant as well. So we're able to see a good comparison between a normal non-CHERI core and a fully enabled CHERI core. So. Okay, and I think this is where I left the last talk at CHERI Tech. And you can see, so we were looking at EM Bench, and we'd done a lot of improvements to get on this. So this was a comparison between the non-CHERI results and the pure cap results. So, and generally we're getting up there, making pretty good improvements, apart from obviously the two on the right, which, yeah, don't look so good. There was a question on the last talk as well as what was the cause of this. And we speculated at the time it was to do with global variable handling. So in fact, we dug into the code a bit more and it actually was global variable handling. So we picked one of the benchmarks here, CRC32. It's a very, very tight nested loop call of an access to an array, global array that had been defined. So in the non-CHERI case, we only had one loads accessing that array. In the CHERI case, we have multiple loads, and really that is the biggest difference of it all. That additional load in a very tight loop meant that we were having a significant slowdown compared to the non-CHERI case. And just to prove it, we have the original sort of non-CHERI version, the pure cap one in red there in the middle. We basically hoisted out the global accesses out of those very tight nested loops. And yeah, unsurprisingly, we recovered most of the performance on a pure cap system. So it does indicate we're going to have to maybe look at things in the compiler and put proper costing in for use of global variables. But we would expect that to be able to pull the performance up again. We've started some very early optimization work in globals. This isn't actually to show, the performance so far on it. This is more to show that whenever we change things in the compiler, it's not as easy as suddenly all benchmarks improve. So this is actually spec 2017. And it's just to show that once you put an implementation for something, you improve it in some benchmarks and inevitably performance tends to drop slightly in others. And a lot of performance optimization is basically a compromise. It's picking the best ones on a generally large set of software. So, I mentioned in the previous talk too about compiler updates, and we were seeing performance increases whenever we were updating the compiler versions. So we actually went back through all of our previous compilers and ran the spec benchmark on each one and looked at sort of what was happening there, the sort of performance we're getting. It's quite obvious in LLVM that we're getting a pretty decent upward trend in performance just from the update of the performance of the standard LLVM itself. So obviously there's not many specific CHERI LLVM performance improvements in this, but this is just a general compiler. The interesting thing here is, well, there's two things. First of all, we added instruction scheduling for our dual issue between what you can see as 19.0 and 19.1 there. So you can see that makes an impact. Something could be done on the CVA6 now with dual issue. I would expect to get similar results. And then the other thing you can see is effectively the error bars here are showing the sort of range and the difference of the impact of all the various optimizations. And it's interesting to see as we go to newer and newer compilers that the difference, as I say, that sort of compromise between improving the code and actually pessimizing it slightly becomes more and more extreme. So at the moment we're about to start 21, LLVM 21, we'll move to 22. It'll be interesting to see if this sort of trend continues or if it narrows down again. So we've also been looking at things like optimized string functions. So previously we'd looked at optimizing memcopy, memmove, memset. We've now gone on to the other string functions. So obviously in non-CHERI systems, there was already optimization. But for CHERI systems, we were effectively relying on byte loops, which were not very good. So we decided to make all of the string functions suitable for CHERI. We also added in ZBB support as well to accelerate them. Generally because it's, we're looking at application cores, RVA 22 and 23 both support ZBB mandated. So, and you can see already particularly on the longer transfers, we get very substantial performance increases. We've still some work to do. Strcomp on short sort of comparisons needs a bit of extra work, and well, that'll affect our dry stone benchmark results, for instance, because it's very Strcomp heavy. So we'll have to look at optimizing that a bit better. But on the whole, it's looking pretty positive. I mentioned too the memcopy, memmove, memset as well. So these are good sort of general across the board optimizations. So this is the spec benchmarks, again, spec int ones, showing the improvement with the optimized memcopy, memmove, memset. So again, on the whole, generally across the board, good improvements. Some of the benchmarks, as you expect, as I said, have a slight drop in them, but very marginal. So we'll keep those ones. So going on from here, we're looking at, okay, how can we get more information about running beyond just the benchmarks, general Linux software, how can we start to look at performance? So CHERI BSD has already had performance measuring software. We've now got perf running under Linux. So this is able to use the hardware performance counters inside the core itself to get a lot more information on what's happening. We've been able to tie this in with recent work we've done too on tracing within the Linux kernel. So we can get function level performance information and hardware breakpoints that we can do continual snapshotting as well. For CHERI specifically, we've just added in support for the performance counters in our tag controller unit before DDR. So we can start to look at tag and capability movements within the system as well, which will hopefully give us a lot more insight to how software is using capabilities and if there's any opportunities we can use to improve things here. And this is just a quick example of a perf run. So you can see here we have hardware performance counters linked to capability and non-capability loads and stores. So we can track those now within applications. We can also get more, particularly for us of interest, is cache behavior as well. As John was mentioning, the cache is very important on CHERI. We don't know yet whether, for instance, expanding the size of cache line would help. I suspect in capability heavy loads it would, but again, the sort of thing we'll need to look at. So we've also been doing other stuff as well. We've just started looking at the muzzle memory allocator. We noticed that hash function wasn't great. Made some modifications on that. Looked really good on the QMU in terms of instruction count and stuff, but when we put it on the real hardware, yeah, it didn't look so good. So we're trying to work out why. In terms of where next, well, now that we have perf, and we're also expanding the sort of size and complexity of applications we can run, we'll do a lot more work on a broader set of benchmark applications, really, under Linux. As I said, we're looking to understand more about spatial and temporal properties of capabilities and whether there's stuff we can do there to optimize, particularly for things like revocation as well, whether we can use the knowledge gain to help us there. And as I mentioned, cache impact as well, because we believe at the microarchitectural level, that's probably a very big impact. Well, we know it is. We'll continue to update LLVM, as I said, moving up 21, 22, align with upstream, and hopefully align with the CHERI at work as well, so we have a consistent compiler. We would like to start looking at specific LLVM optimizations as well, and I know Cambridge has been doing some work on this too, so we'd like to align on that. And generally, yeah, we're looking at very much a data-driven approach for optimization, but we're hitting the low-hanging fruit at the moment, and then we'll start to look at specific use cases and applications. So, okay, thank you.
That's great because each time you come, you have better numbers. So
yeah, exactly.
You'll come next time.
If it goes down, it's not worried. Yeah.
So, questions for Carl? Wave the hand. Oh.
Nice. Do you have like a wish list of instructions you'd like to add to the ISA, maybe in like a future extension, or are you limited just to back-end improvements?
No, that's interesting. Well, we are looking at, one of the things we're just starting to look at is the ISA, and actually the use of the instructions, how commonly they're used, whether they're, can we do like macro op type collapse of operations and stuff like that. So we've only just started that work, so can't say for sure anything yet, but there are indications. I mean, we do see patterns at the moment. I suspect there will be opportunities to put in additional instructions. I mean, we know whenever we created the CHERI RISC-V set, we deliberately cut out a lot of the instructions that had been there previously in the V9 specification. That were aimed at sort of some optimizations, but yes, I suspect we'll end up putting some more back in. Okay. Oh, thank you. Mind your head.
I'll pass it down. Yeah, so on one of the things you highlighted was the additional cost from GOT indirection. How much? So CHERI, as you say, adds extra indirection where it wasn't needed before.
Yeah.
How much of the performance overhead that you see do you think is due to the fact that there is indirection versus just the microarchitectural structures like caches and TLBs perhaps need different tuning for their sizes now that A, capabilities exist and are bigger, and B, more of them exist in things like GOTS?
That's an interesting question, actually, and I'm not sure I know the answer to it. I mean, we know there's a cache hit, obviously, every time we're taking this indirection, even on the L1 cache. It's notable. I mean, the thing with the micro benchmarks is they exacerbate any effects that there may be. you know, it's hard to separate it on bigger benchmarks like spec or something like that, but something interesting to do. I do suspect that improving the cache for capabilities is probably going to get us a lot of that back, but yeah, I can't say for sure yet. So yeah, it's a good question though.
Thank you. No more questions? Okay, so thank you very much, Carl.